Что не получается включить трансляцию. О. So let's hope it works. Let me recall for the third or fourth, but hopefully last time, what we're dealing with. So we have a basis u lambda in the whole algebra, and we set v n, or maybe r, is u1 to the power r. And then we set v lambda transposed is the product of v lambda transposed first, and so on, v lambda transposed second, and so on. And then we want to express this basis via that basis, namely we say that this is equal to the sum over mu a lambda mu u mu. And well, these are certain particular structure constants of the whole algebra, and we wanted to prove that the structure constants of the whole algebra were polynomial in Q, in the cardinality of the residue field of our ring O. Last time we reduced this statement, this miraculous whole theorem, to the proposition. Maybe it was not numbered, or maybe it had numbered 1. That for partitions lambda and mu and compositions alpha equivalent to mu and beta equivalent to lambda transposed, this coefficient a lambda mu is a polynomial in Q in the cardinality of the residue field, namely the sum over all arrays Q to the power d of a. So a, an array of shape alpha and weight beta. But this array must be strictly row ordered. Okay, so we deduced our theorem from this intermediate proposition, and now we are left with proving this proposition. Sorry. So to prove this proposition, we somehow prove it by induction. We reduce it to some yet more particular case of these lambda and mu. So to this end, we make a definition. Namely, we say that beta lies inside alpha, a composition beta lies inside composition alpha, if alpha I minus 1 is less than or equal to beta I, less than or equal to alpha I for any I. And then we set the distance from alpha to beta is equal to the cardinality of the set of boxes with coordinates ij, such that beta I equals alpha I and beta j is equal to alpha j minus 1, and also j alpha j is strictly less in the lexicographical order than I alpha I. So maybe I have to recall this lexicographical order. So we say that I j is less than I prime j prime if j is less than j prime, or j is equal to j prime, but I is bigger than I prime. Okay, so this was our definition, and now let me formulate the following lemma. I forgot if lemmas were numbered, and what is its number. If somebody knows, please tell me. So let alpha and beta be compositions. And the length of beta is r. So there is a bijection between the set of strictly row-ordered arrays of shape alpha and weight beta, and the set of chains of compositions. The first one is 0. It's alpha 0. Then it lies inside alpha 1. This lies inside alpha 2, and so on. This is alpha. But well, sorry, let's move here. The total size of alpha I minus the total size of alpha is beta I for any I. And under this bijection, d of A goes to the sum over all I, the distances from those neighboring compositions. Okay, so the proof of lemma is a bijective proof. Namely, an array A goes to the chain alpha I, where alpha I is by definition the set of boxes where the value of this a function lies in 1 and so on I. Okay. So if you recall what is a strictly row ordered array and everything else, say the definition of this D of A, then you'll see that this is the desired bijection. Okay, so this lemma is considered proved, and now the proposition in question, proposition number 1, follows from proposition maybe 3 or whatever. Next time we did have some more propositions, yeah? By induction. Yes. Proposition 3, I'm going to formulate momentarily, right now. But I remember that last time we had some other proposition after the first one. So I guess this should be numbered 3. So proposition 3 says that assume the size of lambda is the size of mu plus r, and alpha is equivalent, composition alpha is equivalent to our partition lambda. Then the structure constant of the whole algebra, mu, and then r ones, so 0 module lambda over O is equal to the sum over all compositions beta lying inside alpha, q to the power d of alpha beta. Okay, it's just plugging into lemma. This is lemma 3. Great, thank you very much. Okay. So we made a lot of reductions and finally reduced our theorem to this statement, and somehow now there is nowhere to reduce. Now I have to just to prove this. So take an O module M of type lambda, and then by definition the structure constant in question is equal to the cardinality of the set of submodules n inside M of type 1 to the r, and co-type, meaning that the quotient is of type mu. Okay, this is just definition. But you see, since the type is 1 to the r, it means that n is a trivial module. A trivial r, so to say, it's of length r. So the so it is an elementary module of length r. So in other words, n is an r-dimensional k vectors subspace, and K is the residue field in the circle of M. Circle of M is the maximal trivial submodule. Well, let's call it S. Okay. So, in other words, N is a point in the Grassmannian of r-dimensional subspaces in the vector space S. Okay, and we have to essentially count this. We already discussed this last Friday that this count is really a polynomial in Q. Okay, so recall that the whole Grassmannian is the union of Schubert cells, and those Schubert cells are numbered by a certain subset J. I will tell momentarily. So we have a set of indices like this, and take a basis V sub I. Well, maybe it's bad that this V is the same as this V, but another name for a basis element could be U, which is also used, or E, which is also used. So no. W. Okay, let's try W. Though in 10 minutes we'll have another W. Sorry. Okay, and now this J is a subset in I of cardinality R, and now the Schubert cell J is well, it has coordinates. First of all, it's a cell in a fine space. So coordinates are Cij in our residue field, such that J lies in J and I lies in the complement, but it is bigger than. I is bigger than J. Okay, and such a collection of numbers goes to a vector subspace with the basis Wj plus sum over I, Cij Wi, okay. The cardinality of such a Schubert cell is q to the power d of j, where d of j is the number of pairs ij, such that j is in our subset, I is in the complement, and j is smaller than I. Okay. So now our module M, we started with of type lambda, was a direct sum over all I of certain cyclic modules, and the annihilator of xi was the alpha i's power of the maximal ideal. Alpha is our composition equivalent to lambda, the type of M. So this is not necessarily ordered in any meaningful sense. Now we set I is the set of indices with alpha I bigger than 0, the meaningful indices. And Wi, the basic element, is pi to the power alpha I minus 1 times xi, where pi is a uniformizer. That is generator of the maximal ideal in our ring. So then Wi really do form a basis of S, of our circle. Yeah, it almost kills. The next power would kill xi. So it lies in the circle. Now we order I as follows. We say that j is less than I if j and alpha j is less in the lexicographical order than I and alpha I. Okay. Now, finally, the subsets j inside of I are in bijection. With the chains oh no, sorry, not chains, just compositions beta inside alpha, namely to a subset J, we associate beta such that beta I is equal to alpha I minus 1 for I in J, or beta I is alpha I for I in the complement. Okay, so then by definition, we will have that the dimension of this cell, of this Schubert cell, is equal to the distance between alpha and beta, and all the submodules and in this Schubert cell in the Grassmannian. Have the same cotype mu that is equivalent to beta, and that's it. So we did count the number of desired submodules, and it is just the Grassmannian, so the count is polynomial. So we are done. Congratulations, after just 1 week. And maybe one corollary, which is in your home assignment, I guess, in the latest one for April, whatever. Yeah. That the structure constant of this type we just computed. So on the one hand, it was a certain sum of monomials, like there. So manifestly polynomial with positive coefficients, positive integral coefficients. On the other hand, it can be written as a product. So it's q to the power n of lambda minus n of mu minus n of 1 to the power r. We know that the leading coefficient must be of this, that this must be the degree. And now the product of q binomial coefficients, lambda I transposed minus lambda I plus 1 transposed, mu I transposed minus lambda I plus 1 transposed with the base q inverse. Yeah, and the q binomial coefficient is defined as phi a of q over phi b of q, phi a minus b of q. And phi is like q factorial. Okay. Well, and the proof is that the points of in Grassmannian can be counted in two ways. One is most classical, another just by partitioning two cells. So the q binomial coefficient, which is the number of points in Grassmannian of r in k to the n, is the sum over all the subsets of q to the power d of j, where the cardinality of j is r, cardinality of I is n. Okay. So that's it. We did finish the proof of whole theorem, and as I said, this theorem implies that the whole algebra is isomorphic to well, how to say it, to lambda of t, well, specialized to t equal q, so to say, and the natural basis u lambda here goes to some basis there, which is called the whole Littlewood polynomials. And now so these whole Littlewood polynomials are some t analogs of Schur functions. And as the Schur functions play a prominent role for the computation of characters of symmetric groups, those whole Littlewood polynomials play the similar prominent role for the computation of characters of GL. Namely, they will be the values of, sorry, not they, but the transition matrix from those to Schur functions will be formed by formed of constant polynomials, and the constant polynomials will be the values of induced characters at unipotent classes. So we'll do this all in April, but today we will start some basic study of whole Littlewood polynomials. First we will define them in purely symmetric functions realm, and then later on we will identify them with the images of those u lambdas. Okay, first we forget about everything we did last week, maybe last 2 weeks, and study those polynomials. Well, is this? So the definition is somehow similar to the definition of sure functions, like the ratio of two alternating functions, and some alternating function divided by van der Monde determinant. So, well, well, we fix a partition lambda, and first, well, when we define the sure functions, if you remember, we first fix the number of variables, n, and then we prove that it stabilizes somehow. But we will need to use some particular van der Monde determinant n by n, so n is fixed at the moment. And here too, n is fixed, so this n is the length of our partition. But this lambda can have some zeros. For example, it can be 0 at all. I mean, the length is not more than n. Okay, now, well, delta is sometimes rho, maybe, is this partition like this, and A delta, the van der Monde determinant, okay, so that, well, S lambda is A lambda plus delta over A delta. Yeah. And now we define R lambda of x1 and so on, xn and t. Well, t is this extra variable as I just erased. Is in the t deformation of symmetric functions, and x are just the variables of symmetric functions, and so this R polynomial is not the whole Littlewood polynomial. It is some intermediate thing which is worse, which will not stabilize, and we will renormalize it and obtain whole Littlewood polynomials. So this is the sum over all permutations x1 to lambda 1 and so on, xn to lambda n times the product over I less than j, xi minus t xj over xi minus xj. Okay, or else we can rewrite it as 1 over the van der Monde determinant, the sum over permutations, epsilon of W, permutation of x1 to lambda 1 and so on, xn to lambda n, and the product over I less than j, xi minus t xj. So we just have this common denominator, and I put it before the brackets. Okay, and then we see that that this is something alternating, because well, I took some function and alternated it, and so it's divisible by some basic result by the van der Monde determinant, and when I divide, I obtain some symmetric function. Okay, and this symmetric function, so well, this is alternating, and hence this ratio is symmetric. And well, the symmetric ring does have a basis of sure functions, so it can be written in the basis of sure functions. So it is the sum of u lambda mu of t, s mu of x1 and so on, xn. Okay, for some polynomials u lambda mu with integral coefficients. Okay, now then claim 1 is that this transition matrix is upper triangular, so u lambda mu is 0 unless the lambda and mu have the same size, and lambda dominates mu, and finally the diagonal term u lambda lambda can be computed explicitly. This is well, yeah, again, I have to call it v lambda of t. I'm sorry, though we had some other v lambda of t, but maybe it's not so important notation. So this v lambda of t, by definition, is the product of v mi of t. I mean that lambda is this exponential notation, and v m of t is the product over 1 minus t to the I over 1 minus t, or else it's phi m of t divided by 1 minus t to the power m. But m can be 0. Yeah, because our lambda can have zeros, 0 to the power m0, 1 to the power m1, and so on, so that the sum of I mi is n. Okay. Yes?
What is epsilon in this formula?
Epsilon is the sign. Maybe I should write -1 to the power w. Okay, so we will prove this claim. Maybe before we prove, I formulate some particular case. For lambda equals 0, on the one hand, well, R lambda will be 1 and S lambda will be 1, but there will be no trivial formula for that. So we get an identity that the sum over the symmetric group permutations of the product over I less than j, xi minus t xj over xi minus xj is equal to Vn of t. Okay, and maybe let's recall this identity. We'll use it afterwards. So, well, let's write the numerator. Just expand the numerator. And we get the sum of the products over I less than j, x I to the power r ij times minus t xj to the power r ji, and the sum is taken all the matrices rij again fermionic, if not stochastic. So the matrix entries are 0 or 1, and we know that pardon me? All of the matrices, yes, but we know that the diagonal elements are 0, and rij plus rji is 1. Okay, this is the tautology. And now we set alpha I is lambda I plus the sum over j rij, and d is equal to the sum over I less than j r ji, and finally a alpha is the alternation of x 1 to the power alpha 1 and so on, xn to the power alpha n, just as in the theory of sure functions. So then we get that R lambda is the sum over all matrices Rij, as here, minus t to the power d, a alpha, a delta inverse. We divide by the van der Monde determinant. Okay. So those parts of alpha certainly are all different. Otherwise, the alternation gives you 0. So we can assume alpha I are all different, distinct. Then let us order them well in decreasing order. So we rearrange them. There is certain permutation W. Alpha W of I is mu I plus n minus I. So the alpha Wi strictly decrease, and we can subtract this, and we will obtain some partition mu. Those mu will decrease, but not strictly, not necessarily strictly. Okay, so for some, well, maybe for a unique permutation W and partition mu. Okay, so then certainly a alpha divided by the van der Monde determinant will be epsilon of W, or as we write it, minus 1 to the power W times the Schur function S mu. And it remains to check that mu is less than or equal to lambda. Yes. What exactly?
This A alpha, A delta is
Uh-huh.
-1.
It is just definition of the Schur function. Just definition. Okay. So let's set Sij is equal to R W I Wj. Then Sii is 0, and Sij plus Sji is 1 again, and mu I plus n minus I is lambda Wi plus the sum over j Sij. Okay, and it follows that for any k less than or equal to n, we have mu1 plus so on plus mu k is lambda w1 plus so on plus w k plus the sum over I less than or equal to k, the sum over j less than or equal to n, Sij minus the sum over I less than or equal to k of n minus I. Okay. And now we can rewrite this, the double sum. Sij is the sum when both I and j are less than or equal to k, plus the sum where I is less than or equal to k, but j is bigger than k. Okay, and then we get the sum of all integers up to k minus 1 plus the second half okay, but at least this is not more than the second half is not more than k times n minus k. And then when we sum the two things, we get just this. And this is good because it means that the sum of mu's up to k is less than or equal to lambda w1 plus so on plus w k, which is at most lambda 1 plus so on plus lambda k, because lambda was ordered, it was a partition, right? And hence mu is less than or equal to lambda. Okay, this is what we wanted to prove. No, we also wanted to find u lambda lambda. So maybe it's too early to finish the proof. So again, from this we also see that lambda can be equal to mu if and only if lambda wi is equal to lambda I for all I. And also Sij equals 1 for any I less than j. So it follows that u lambda lambda of t equals the sum over all permutations over minus 1 to the power w minus t to the power d. Sorry, it's not over all permutations. Sorry. but over the permutations preserving lambda over all w such that w lambda equals lambda, and d was the sum over I less than j r ji, which is the sum of I less than j s w I wj only sorry it's the inverse permutation, sorry, it's w inverse of j and w inverse of I. So yeah, S was defined this way. Okay, so this is the number of I less than j such that W inverse of j is less than W inverse of I. Okay, and well, this is the number of L less than K such that W of K is less than W of L. Okay, maybe L is a bad idea, but what can be better? Maybe M. Oh no, M is also bad. Maybe. Well, let me K prime maybe. K prime such that K prime. So this is called length of W, right? Number of disorders. Okay, and also minus 1 to the power W is exactly minus 1 to the power L of W. Of W, yes. Yeah, well, K is bigger than K prime, but W.
We use W both for this fifth permutation and for here we sum all W, and so it's a bit mixed up. Yes, here you mean this.
Well, somehow I so I here I use all the permutations, yeah, which preserve W, preserve lambda. I don't know what to say. So I think it's okay to still call them W.
Here we mean this, the normal disorders of this.
No, we're summing over all the permutations, and
So this D
so what's the question?
I'm just lost.
Sorry. So this. So given lambda, we have its stabilizer in the symmetric group. For example, if lambda is 0, then the stabilizer is the whole symmetric group. Or if lambda is consists of all distinct parts, then the stabilizer is trivial. Yeah, and to find this coefficient u lambda lambda, we need to sum certain expressions over this stabilizer of lambda, yeah, or parabolic subgroup in the symmetric group, right? And these expressions are certain polynomials in T. Yeah. U lambda lambda of T is the sum over the stabilizer of lambda of expressions plus minus T to the power D of W. Okay? And the first observation is that there is no plus minus, that this minus 1 cancels out that plus minus 1, because they are both minus 1 to the same power. So it's just the sum of those. Now, S lambda is the product of S mi's. Yeah, it depends on the multiplicities of the parts, and we just want to check something for one factor. So it remains to check that the sum over all permutations in some smaller group Sm, Smi, T to the power L of W is just Vm of T. Okay, and this is a very interesting identity. It is a generalization of what we had for Grassmannian before. Instead of Grassmannian, it is about complete flags. So we count points in complete flags over k to the power m in two ways. So first of all, the complete flags, they consist of flags 0 in f1, in f2, and so on, in fm-1, in fm that is equal to km, and the subscript is the dimension of the corresponding subspace. So we see that there is a projection from this space of flags, say, onto the space of hyperplanes, and the fiber is just all the flags in m-1 dimensional space, right? So the flags of Km project onto projective space m-2 oh, sorry, m minus 1. M minus 1. And the fiber is flags of k to the power m minus 1. So we can inductively find the number of points because we know the number of points in the projective space, and we just multiply. So we see that this is the number of points in P m minus 1 of k times the number of points in P m minus 2 of k, and so on. And this is just Vm of t. Okay. So this is the multiplicative right-hand side. The additive, pardon me?
Where's T here?
Oh, sorry. T is Q is the number of elements in our field. And now the left-hand side is again the partition into Schubert cells. So this was the right-hand side, and the left-hand side. We say that the flags is the union over all permutations of the corresponding Schubert cells, and just the number of Schubert cells is the length of W. And probably you had exactly this problem in your January 31st, no? Didn't you? Or nobody solved it? I forgot. It was about something about this, maybe just exactly this, no? Brouillard decomposition, right? Because well, this flag space of Km is certainly homogeneous space of GLM, right? Because any two flags can be taken, and the stabilizer of one flag is the Borel. So it's GLMK over the Borel, well, of K if you wish. Well, M may be also important. Okay, and so if you know that the GL is the disjoint union of over all permutations, B. I forgot how I wrote it. Yeah, just BWB. Okay, because it can be done more economically, but it was written this way. Okay, and each one is, well, this is something, but if you take the quotient modulo Borel, then you get a cell. And this is related to this more economical way of writing. Because, for example, if W is 1, then certainly you don't need Borel on the right of 1 and on the left of 1. It suffices just take one Borel, right? It will be a cell of 1 point. And you can do it the same economical procedure for any. But again, maybe let us
It's only when T equals Q. Why calls for any T? I mean,
because there are very many Q's, right? We know that these are polynomials. Yeah, and their value coincide for infinitely many prime powers. I don't know, what shall I erase? Maybe I shall erase this. So I mean, to be on the safe side, I will give an elementary proof of this identity. Pardon me? So you're asking how to prove it by induction, or what's your question? So what's the question? How to prove it by induction, or? So I can't understand what you say. Do you say it's wrong, or you don't know how to prove it, or what? Well, we're in the process of proving it, if you wish. You want to prove it by induction? Okay, you're welcome. But we didn't prove it yet. We didn't prove it. We didn't finish the proof yet. Elementary. So, no, I cannot. But you certainly are very welcome to try. Yes, on your own. But let me finish this. Yeah. So as you suggest, well, unfortunately, this is the equality what we want to prove. So an elementary proof by induction in M. So set Wi for 1 less than or equal to I less than or equal to M is the permutation transposition of I and M. Just I and M are swapped. So these are the representatives of the cosets. Probably they are called left cosets, but I always have trouble with this. Sm over Sm minus 1. And the length of, pardon me?
If you permute them
Right.
right multiplication,
Okay.
permute them by left multiplication, it's left cosets.
No, it's very convincing, but somehow my memory is hopeless. Yeah, sorry. I'm trying to learn this for 50 years by now, but to no avail. So the length of W prime Wi is the length of W prime plus M minus I for W prime in S M minus 1. And hence the sum over Sm of t to the power length of W is the sum over W prime in as m minus 1 t to the power L of w prime times 1 plus t plus so on plus t to the power m minus 1. But so we essentially just repeat what we said in the previous argument, right? We rewrite the number of points in the complete flags in the product of the similar for smaller flags and for projective space. But we do it not in terms of geometric flags, but in terms of this mysterious left-hand side. Okay, so now we are done. Well, the time is up, unfortunately. Okay, but at least we proved this first claim. And next time we'll continue with the other claims. Pardon me? But certainly you're welcome once again to prove this on your own.